This is Analysis of Time Series, Chapter 16. So we're going to look at financial volatility, and we're going to do some pump modeling. And that's going to lead us towards looking at pump models where there's feedback between the observations and the latent dynamics. And we're going to look at how such models arise and how to fit them. So we're going to start with some background on time series analysis for financial volatility and the kind of analogs of the ARMA framework for this financial volatility problem, which are the so-called autoaggressive, continuous heteroscedasticity and generalized autoaggressive conditional heteroscedasticity models. And let's get started with that, but let's first just review some financial basics. So we've seen in some different situations that returns on investments in stock market indices or large companies are often found to be approximately uncorrelated. And you can think of that as an empirical fact if you take the difference of logs of a stock market index or a large company, that is generally what you find. And one way to look at that is if there were a correlation, then that would be a business opportunity. You could see the correlation, that would give you some predictive power, and then you could make money. And this is why it's hard for that to happen for a large company. If you have, say, a small company or some non-tradable product, then even if you have a sort of small statistical insight into predicting whether it's going to go up or down, you may not be able to make money because of the costs of trading, or it's hard to trade a large volume. But in a kind of liquid or large market, then if these things happen, some investors will pounce and make the money, and that will correct the opportunity. The opportunity will disappear. And so generally speaking, it's very hard to go about trying to successfully predict stock market indices or stock values. But it turns out that you can predict the volatility. You can predict the size of the jumps. You just can't predict the directions of the jumps. And understanding this volatility is important for understanding risk. Obviously, the larger the jumps that are going on in the market, the larger the risk of being involved in the market. So here's the S&P 500 daily data that we saw earlier. Runs from 1950 up to getting close to 2020. And we see, well, on the right, we see it on a log scale where it looks something like a random walk with drift, as we saw before. Now, if we write the index value as Z, then we can let yn star, the data, be log zn minus log zn minus 1, and that's called the return, the difference of the log of the index. And this has negligible sample autocorrelation, but if you look at the absolute deviations from average, then that has considerable autocorrelation. And so here is the here's the fit of the d-mean daily return from the S&P 500 index. This is for the years 2002 to 2012, because we're going to compare with a model fitted by a 2014 paper by Bretto. And so let's use the same data. Okay, we can certainly see from this periods of high volatility. And so it's worth thinking, is it appropriate to fit a stationary model to this time series? Do we need a non-stationary model? Well, you might be inclined at first to think that this is evidence against stationarity, but it could be that these periods of high volatility are themselves generated by a stationary process. Sometimes it's highly volatile, sometimes it's not, but that process is stationary. And so let's try to write that down. So volatility peaks, which are here, and maybe there's one at around 100 days. There's a big peak at around 1700 and maybe something else at around 2400 days. These may seem to violate stationarity. However, if volatility follows a stationary process, let's say it could be consistent with stationarity. Okay. So here we have the famous autoregressive conditional heteroscedasticity model and its generalization. And I'm just going to introduce these models briefly. This introduction follows the reference to Coperthwaite and Metcalfe that you can look at if you want more on this. There's also more on financial models in Shumway and Stouffer. So an autoregressive conditional heteroscedasticity model, that's something of a tongue twister, has this form where Vn is the volatility. So you multiply the white noise by root Vn so that its variance is Vn, and then that gives you a model for the return Yn. And then you need to decide the form for Vn, and in the ARCH model, Vn depends linearly on the squares of the previous returns. And this means that if you look at this a little bit, you'll see this means that Yn squared is ARP. It's not a Gaussian ARP though, but it is an ARP, and so this whole process is in fact not Gaussian. It's called a Gaussian arch if the epsilon ends are Gaussian, but they're still, Yn is still not Gaussian because the epsilon n is multiplied by some other random variable. That product is generally going to be non-Gaussian. So that's the ARCH model. In practice, people often fit a generalization of that, which I guess ARCH is autoregressive volatility, GARCH is kind of autoregressive moving average volatility. And so here's the GARCH model, where again Vn is the volatility process, and Vn depends linearly on previous volatility and previous squares of returns. And so this is a model, you can fit it using the GARCH function in the T-series R package. That's one way to do it. And so here's some code to fit the GARCH model, and it'll go ahead and calculate the maximum likelihood of the GARCH model for you. It's a little bit of a trick to get the maximized log likelihood out of it. If you just do log lick of the fitted GARCH object, you won't get it, which is kind of counterintuitive. You have to go dig into the package and then you can get it in this way using the loglit.garch function. And well, once you have a likelihood, then you can do your likelihood inference. This is actually not quite a true log likelihood. It's actually a conditional log likelihood given the first max PQ values. But I think for now we're going to treat it like a likelihood. And then here's just a little kind of refresher question, just general applied statistics, nothing to do with GARCH models in particular. I have given this log likelihood to 5 significant figures. Normally, we don't give numbers to 5 significant figures. Maybe we give them to 3 significant figures. Here I'm doing it really not to 5 significant figures, but to 1 decimal place. And it's worth thinking a little bit why that's the right thing to do. So for log likelihood, when we have log likelihood, we interpret differences rather than absolute values. Differences have more meaning than absolute values. And order 1 decimal place. Well, order 1 decimal place of log likelihood is statistically important. In some sense, it's, most of the importance of the likelihood is on the unit scale, but it's worth carrying maybe 1 decimal place just for a little bit more attention to detail, but the 2nd or 3rd decimal places are usually not relevant to the statistics. Okay, so we can now carry out all the tools of likelihood-based inference for GARCH models. We can do profile likelihood, likelihood ratio tests, AIC. We can simulate from the GARCH model if we want to. Very quickly, without really saying more about GARCH than I have done, you're able to use that as an extra tool. But GARCH has a very similar limitation to ARMA models in the sense parameters don't have a clear interpretation. As the GARCH model gets bigger, you think, well, maybe it more or less fits the data, but so what? It may be useful for forecasting as a sort of black box model, but it's hard to ask and answer questions about the structure of financial markets by just fitting a GARCH model. And so we want to think about how to model the financial market and its volatility more mechanistically. And so the starting point for that is what I'm going to look at here is what's called a simple stochastic volatility model. And the idea of a stochastic volatility model is that you model volatility as a latent stochastic process. And so you observe the returns in an ARCH or GARCH model. The variance of the returns is an exactly specified function of the previous returns. In a stochastic volatility model, the volatility is something that moves around and you don't get to see exactly what it is. It's a latent process. And here is a basic stochastic volatility model. The reference Kastner 2016 is a kind of review of stochastic volatility models in the context of software you can use to fit them. We're going to just fit them by putting them in the POMP framework that we've used in other situations. Okay, so XN, the volatility is non-negative, so it's often natural to model log volatility, and XN here is log volatility. And so if that's a variance, if you take its exponent, you get the variance. Then if you square root it, you get the standard deviation, which you multiply by the noise process epsilon n. And here, volatility follows an autoregressive process. And I mean, this is a Pomp model, so we can fit it using our tools that are fairly standard by now, but we can also use the flexibility of the Pomp framework to see if we can do better than this. And that's what we're going to do in the next section.